Good morning, I'm Francois Fouchier, Screening Specialist at Multitech. The topic of this morning discussion is the removal of fines using screens. Irrespective of the mineral that you recover, the removal of fines is an important step in your process. The fines fraction can be removed by utilizing vibrating or static screens. The optimum solution will depend on the correct combination of screen and screen media. The next few slides I'm going to speak about the contribution of the screen, and this will be followed by a presentation on screen media that is suitable for fines removal. The following topics will form part of our discussion this morning. We're going to have a look at the reasons why it is necessary to efficiently remove fines from your process. We're also going to have a look at the duties that require efficient fines removal. We have to pay tribute to screening concepts from the perspective of the vibrating screen. We're also going to spend time looking at the multi-slope screen. Water is your best friend when it comes to fines removal. We're going to spend time looking at the role of water. And we're also going to have a look at the dewatering screen. It's a screen that is used not to remove fines, but to capture fines. Finally, we will have a look at the application of sieve pens, static screens, and trommels. As I've said before, Roy Rose, who's Vice President Screening at Multitech, will detail the media that is required for fines removal. To lay the foundation for our talk, we need to remind ourselves why it is important to remove fines. If you consider that the fines content in the plant feed could be between 10 and 15%, you can obviously increase capacity by removing the fines fraction. The effect of fines on crusher liner wear is well documented, and this is another reason we need to get rid of the fines fraction. Consider that you sell stockpiles of iron ore or coal, and there's misplacement fines captured in these stockpiles, and consider the penalties that go with this, even more reason to remove fines from the process. We know that process equipment is sized to be efficient within a certain particle size range. It could be a cyclone, it could be a spiral, and it's the purpose of the screen to prepare the feed in terms of removing the fines that is sent to downstream process equipment. One is wasting energy when you treat a size fraction that does not add value. And finally, imagine operating a flotation plant and you do not remove fines. What is the effect on reagent cost in terms of not removing the fines fraction? We can define 6 typical screen duties, and 3 of these deal with the removal of fines. To name them, the desliming screen, the heavy media recovery screen, and the dewatering screen. Before we can look at the contribution that the screen or screen media can make in fines removal, we need to remind ourselves of a number of important screening concepts. The first of that is stratification. Remember that fines cannot be removed as long as they're trapped in the screen. Stratification, or the rate of stratification, is influenced by 5 factors. We're going to look at the bed depth, the material travel velocity, that is G-force dependent. We're also going to have a look at the stroke characteristic of the screen. There's water content in feed, and finally the effect of particle size distribution on stratification. The second important concept is that of bed depth, and this is the distance that a fine particle has to travel through the bed before it is likely to encounter a panel aperture. So when screen OEM size screens, they place a limit on the bed depth at the discharge end. For classification and sizing screens, most OEMs limit the bed to between 3 and 4 times aperture size. However, when we're speaking fine screening, the golden rule is to limit that bed to between 6 and 7 times, not the aperture, but the mean particle size in the feed. We also need to be practical. Consider operating a coal plant and the run-of-mine feed has got a lump size of 50 ml, which is quite common. Obviously, in that instance, we're not going to limit the bed to 6 or 7 times mean particle, but in this instance, the lump size become the discharge bed limit. When we talk dense medium screens, the DSM manual does not directly state a limit on discharge bed. In this case, it's possible to back calculate the discharge bed from the capacity factor that we calculate. Remember, that's going to give you tons per hour per meter screen width. So we back calculate the discharge bed using a low G-force 6-pole motor drive, which was the standard at the time. Finally, if you need to calculate the theoretical discharge bed on your screen, it is just simply the oversized tonnage divided by screen width, bulk density, and material travel velocity. We know that the combination of screen speed and stroke gives us the G-force for the screen. Now, since G-force has a direct influence on material travel velocity, the OEM can use the G-force as a tool to control the bed depth. Furthermore, as stroke has got a dramatic effect on material travel velocity, it's common practice for the OEM to make use of a 6-pole motor on any given screen size to increase capacity within the limit of the discharge bed. Now, this slide shows us the influence of screen drive on material travel velocity. Should we use a 4-pole drive as the base, you can see that the increase by converting to 6-pole drive is dramatic, as we can increase material travel velocity by close to 45%. Remember the benefit of this? This allows more tonnage within the bed depth constraint that was set to guarantee an acceptable rate of stratification so that we can benefit fines removal. Likewise, if we change to 8-pole drive, we can increase travel velocity by another 30%. OEMs will also consider inclining screens as an option to increase travel velocity as a tool to increase the rate of stratification. You can see that a 5-degree inclination can increase material travel velocity by almost 20%. This is the famous Multitech drainage rate graph, which has really traveled the world. It provides drainage rates in cubic meters per hour per square meter for various screen panel apertures. I'd like to caution you that when it comes to the drainage rate of medium, these figures are considered optimistic if you consider that the test work was done on a gold plant slurry with a solids content of 50%, which is regarded as a free-flowing slurry. There are companies in industries who have conducted drainage rate test work specifically on ferrosilicon or magnetite, and it is wise to rather consider this data when it comes to drain and rinse screens. Before we look at the modern multi-slope screen, let's pay tribute to those before us in history. For many decades, this arrangement on screen was used for desliming and drain and rinse operations. You can see that the sinks and the floats product from the cyclone is fed onto sieve bends. The sieve bend will do the initial desliming operation. The underflow will connect with the screen underflow, and the oversize of the sieve bend will be fed onto the screen. You will continue with the removal of fines. On screen you have a typical horizontal screen fitted with 6-pole drive. Looking at the feed arrangement, you can see it is a split floats and sinks screen, and for this sort of operation you can expect a travel velocity in the region of 600 meters per hour. Now if you think back to the discussion on stratification, and you note the high material bed at the feed end, you can see that very little work is done in zone 1. Once stratification has occurred, 80% of the solids is removed in zone 2. All of this has changed with the introduction of the multi-slope screen. These screens are high capacity machines. Why? Because of the quick stratification that takes place. And why does this happen? Because we almost end up with a monolayer thick bed of material on the top slopes. Why is this possible? Because of the high travel velocity that these screens generate. And once again, why is this possible? Because of the steeply inclined top slopes. So really we can't talk about this topic this morning without paying tribute to the SIP Technique multi-slope screen. Now look at the fines profile that we get from the multi-slope or the banana screen. It's only towards the discharge end where the material travel velocity slows down and the bed increases, but you can see that the majority of the work is done on the top slopes where we have 3 to 4 meter travel velocity. There's therefore no doubt that we have a very effective machine in the multi-slope screen for the removal of fines. I know that OEMs rate the capacity of these machines up to 50% more compared to equivalent size horizontal screens. In the African market, these screens are built up to 4.3 meters wide. If you travel to the large iron ore mines in Western Australia and to the large copper mines in South America, you're likely to encounter 4.8 meter wide multi-slope screens. We spoke about rapid stratification and a low material discharge bed. This is all made possible by the high material travel velocities, which in turn is a result of the steep inclined slopes at the feed end. You're likely to generate between 3 and 4 meters per second on a 34-degree top slope and between 1 and 2 meters per second on a 24-degree second slope. Remember, as far as screen media is concerned, slotted apertures is preferred for the top slopes. As I've mentioned before, DSM is not directly specifying a maximum bed depth when we size DMS screens. However, as the capacity factor C states the capacity per meter width of screen, we can back calculate the depth bed by assuming a low G-force 6-pole travel speed, which was the standard at the time. Once again, the capacity can be increased by using the modern multi-slope screen while maintaining this calculated discharge bed. This is what these machines look like. In picture we have a proud Dave Watson from Vibram-X saying goodbye to a 4.3 meter wide machine which is on its way to a colliery in the Witbank area. As I've also mentioned before, if you travel internationally, you're likely to encounter 4.8 meter wide single deck multi-slope screens and 4.3 meter wide double slope screens. It's not always the case that we want to remove fines to underflow. In the case of the dewatering screen, we want to trap fines in the material bed in order to send it off to the tailings dump. In this instance, the intention is to size a screen that will operate with an 80 to 100 millimeter thick discharge bed. Typical geometry of the modern dewatering screen provides for a 45-degree back window and a 5-degree upslope on the second slope. And as the material slows down and the bed increases in depth, one is able to trap almost 98% of solids. If you've been involved with the sizing of screens, you will know that water is your best friend. The question is, how much is enough? Now, since we're dealing with fines removal this morning, we will go back and consult the DMS manual. As far as these sliming screens are concerned, the water requirement is up to 14 times the solids volume in underflow for a typical feed of 10 to 15% solids. Now, I know that most OEMs regard this as conservative, and it's really not realistic for mines that operate in arid regions, and some of them reduce the spec to 10 times. As far as the drain and rinse screen is concerned, the water specification is highlighted in the blue formula. But let me end off by saying the removal of fines ceases when the last of the water has drained through the deck. Now, Multitech offers a complete range of spray nozzles for the addition of spray water, and for each of these nozzles we can quote flow rates for specific pressures, and we can quote spray widths for installation heights above the deck. And the combination of this data will allow you to design a spray water system which will make the screen just so more efficient when it comes to fines removal. Trommel screens are also considered for fines removal. In picture you see a mineral beach sand site in KZN province. An advantage of the trommel in this duty is the high slurry volumes that trommels can handle. Some of these trommels are up to 15 meters long, and at Multitech we employ a combination of baffles and wear bars and scrolls to establish laminar flow conditions that is conducive to good drainage rate. Also, trommels do not require the type of civils that is associated with vibrating equipment. Grand Kutei is a mineral sand site in West Africa, and this slide shows the installation of rather large self-driven trommels which is still in operation today. Driven trommel screens are not typically used for fines removal, but provided that sufficient water is present in the feed and a good spray pipe system is present, it is a duty that can also be pursued with driven trommels. Over to the iconic sieve bend. Operating as a stand-alone unit, sieve bends are obviously less efficient than screens or trommels, given the short retention time. When it comes to fines removal, these units are often used to increase the capacity of screens. The sieve bend remains a cost-effective and a simple and a reliable scalping solution. Given the short retention time of material on the sieve bend screen, it is critical to have a proper feed chute. At Multitech we have 4 feed chute designs available to ensure that the sieve bend operates efficiently. The static screen can also be considered for the removal of fines. These units are available from 300 mm wide up to 3000 mm wide and up to 6 meters in length. The static screen perform a similar duty as the sieve bend, and they've become more popular over time at the expense of the sieve bend. This is probably due to the fact that they make use of modular screen media, which are more economical, and also the fact that the media does not require frequent turning to maintain the sharp cut point. Following process considerations apply to sieve bends and static screens. Ideally, the feed should not contain more than 30% solids. These units are typically 65% efficient when operated as a stand-alone unit, but 2 units in series can approach 90% efficiency. They are often used in conjunction with a vibrating screen. Sieve pen slots are cross flow. On static screens, the slots are with flow. Removal of fines by means of screening. I'm concluding with the following. Most mineral processes require efficient removal of fines. Both the vibrating and static screen can be efficient fines removal machines. The modern multi-slope screen makes for the perfect desliming and drain and rinse screen. Appropriate screen media needs to be selected to provide for the total solution for fines removal. Good luck removing those small guys. Thank you.